Okay, yeah, today I'm going to talk a little bit about the new file system that we're using for Frontier that we call Orion. It's our latest center-wide file system deployed at the OLCF, and it's the primary storage for Frontier, the nation's first exascalar supercomputer. It's based on HPE Cray's ClusterStor E1000 storage platform. And in this talk, I'm going to be giving a bit of an overview of the hardware that we use in the file system, talk a bit about some of the key points of the Lustre configuration, and then I have some graphs that show some file system performance benchmarks. So a little bit overview of the hardware. The Orion file system consists of, we have 2 MGS nodes, we have 40 MDSs, 450 OSS nodes, 169 LNet router nodes, 12 utility nodes, and 2 management nodes. Each of the 40 MDS nodes, they serve out a single NVMe-based MDT, and the OSS nodes actually have a combination of OSTs. They have 1 NVMe-based OST and 2 hard drive-based OSTs. From a capacity perspective, the MDT storage, we have about 480 drives, make up about 9.7 petabytes of storage there. The NVMe-based OST storage gives us a performance tier that's 11.4 petabytes in size, and that has 5,400 drives. And then the bulk of it is a capacity tier that's 667 petabytes of storage with over 47,000 drives in it. This shows a picture of the storage enclosures that we use in Orion. It basically consists of 2 enclosures. One is called the Gazelle enclosure. It's a single 4U enclosure. It has 24 slots for NVMe drives and 2 controllers inside of it. And then there's the other enclosure called the Mohr controller, which is larger and contains 106 hard drives in it. These enclosures are used in 2 ways. For the SSUs, the scalable storage units, we have a Gazelle enclosure populated with 3.2 terabyte Samsung NVMe drives, and that's chained to 2 of the Mohr enclosures, which are populated with 18 terabyte Seagate drives. And so that provides us one of these scalable storage units then has 2 OSSs in it, and it serves out the in total 2 flash-based OSTs and 4 hard drive-based OSTs. The Gazelle enclosure is also used for our metadata servers as well. In that case, you just have a single Gazelle enclosure populated with 24 drives. In this case, there's 30 terabyte drives, and the 2 controllers then serve as the 2 MDS nodes, and half those drives are used for each of the MDTs. And from a looking at the configuration on the floor, I don't have a picture of it here, but the way it's set up is a single rack, a 50U rack, will have 5, you can put 5 of the OSS or the SSUs in a single rack, and in a single row we'll have 9 of those racks there. And along with those 9 racks for the SSUs, we'll have there's sort of a single central rack that has 4 of the MDU units in it, and that rack also contains things like some of the LNet routers in there, Ethernet switches, slingshot switches, other sort of infrastructure pieces as well. And so a single row of that is what we call a I/O scalable unit, and Orion consists of 5 of those units. For the high performance network, Orion's connected to Frontier via the Slingshot network. This is a Dragonfly topology, which has switch groups connected together with global links. For the storage groups, we have 64 port Slingshot switches. 16 of those host ports, or 16 of the ports go directly to hosts, and we have 16 switches in a single group. So at the bottom I have a little diagram there. It's kind of showing 16 ports. They're called the L0 ones, go to host ports. Then there's the L1 links. That has 30 ports. You have 2 links to each of the other 15 switches in that 16 switch group. And then the L2 ports are used to connect to other slingshot groups. So each row in the Orion file system, we have 5 of those, is its own slingshot group. And then each row that is its own group then has links to each of the, I can't remember how many, can't remember the number of compute slingshot groups, but it has connections into each one of those. We're using ZFS as the backend file system, and we're utilizing the distributed RAID feature of ZFS. We're using ZFS version 2.17 on the MDTs and the OSTs. We're handling redundancy with the dRAID, and here I've shown the dRAID configurations that we're using on each of the things. For the MDTs and the flash-based OSTs, those are in the enclosures with the 24 drives. Those 24 drives are split in half for each controller. And so you have the dRAID setup that uses, has 12 drives, basically 1 distributed spare, 9 data drives, and 2 parity. For the Moose enclosures, we take half the drives in an enclosure, 53 drives in a single Z pool. And that's set up with dual parity. It has 2 distributed spares in it, and uses sort of 11 data drives out of for the 53. And if you're not familiar with dRAID, I've kind of broken down what the numbers mean here at the bottom. For our Lustre setup, we are using Lustre version 2.15 with some vendor patches applied to it. We utilize 2 OST pools for our file placement. We have the performance tier, and that just consists of all the OSTs that are flash-based, and the capacity tier, which is the hard drive-based OSTs. We're making use of the distributed namespace feature, so we, at the sort of the top level of our file system, we spread our project directories across the MDTs. We're only utilizing sort of the remote directories of it. Each project will go to a single MDT. We're not utilizing stripe directories as of yet. And then our file layouts take advantage of several Lustre features. We have DOM, we've got self-extending layouts, and we're also using progressive file layouts. Here's an example of the default file layout we've defined for the file system. We were attempting to come up with a layout that would work for the vast majority of the users. We know a lot of our users get on, they want to compute, and they don't necessarily tune their file striping to their application. Some power users will, but a lot of people just kind of write files and don't touch anything else. So we wanted to come up with a layout that would be reasonable to use for most use cases, allow us to take advantage of the features like DOM and the performance tier, but also prevent people from just like dumping everything onto the performance tier and filling up things. So we sort of settled on this layout where we put the first 256K on the MDTs, then we put 8 megabytes on the performance tier, and anything beyond that then spills over to the capacity tier. And there we actually have 2 components on the capacity tier. Up to 128 gigs, we'll just do a single striped, and when we go beyond that, then we stripe a little bit wider, and we use a stripe count of 8. The reason we chose these things, this was based off some data we had from Summit with file distribution sizes. Based on the numbers we got from that, we expected about 70% of our files will reside entirely on the DOM. Another 18% will fall entirely within the DOM and that first component on the performance tier, and then the remaining 12% will sort of span over onto the capacity tier. But that 12% will still account for 99% of our total use space on the file system, at least if the trend continues and we sort of have the same file distribution as we did on Summit. You'll also notice that with our layout, we've added the -Z option, which is the self-extending layouts. And we've chosen to start with this as a way of guarding against a user who might fill up, prevent filling up single OSTs. If things start to get full, we don't want to get I/O errors, and so this can help with those cases. We don't expect to hit it very often, if ever, but if a OST were to fill up for some reason, This would allow the layout to change and sort of short circuit and jump early to the next component, and the user wouldn't necessarily get an I/O error. For the benchmarks, the first graph I have here is some benchmarks we did for the Orion MDT. This used the MD test program. We have graphs showing all of the, directory and file create, stat, removal, things like that. And this shows how performance has scaled up, going from a single MDT up to 40 MDTs in total. And the graph shows MD test running for a unique directory configuration for each process. That test, I believe, used 1,060 nodes, and we had about 8 threads per node running to generate those numbers. You can see the scaling seems to go quite well. It's not perfect, but we are getting definitely increased performance as we utilize the 40 MDTs there. The little chart on the right is a configuration where we tested out the MD test with the shared directory configuration. In that example, I believe we used a little over 4,700 nodes for that, and with 1 thread per node. You can see we had, file creations was in like about 25,000. File stats was up to like 98,000. Sorry, the 69,000 there. Had trouble reading the small print. The numbers have the shared directory was for like file stats was the 98,000. The single MDT for the unique directory, since the numbers are so small, those numbers I have here, the file stats were about 69,000, comparable. Most of the other numbers for like directory creates and stats were fairly similar, even for like the shared directories. For file creates for the unique directory configuration on a single MDT, file creates were about 45,000, file stats were almost 70,000, and the file removes were a little under 50,000. We ran some benchmarks on the performance tier, so this is just using the flash-based OSTs. The plots on the left, that represents a single scalable storage unit. So if you recall, that involved is basically the storage associated with 2 OSS nodes. And that would be a total of 2 flash OSTs among those nodes. So you can see for the sequential reads, we're getting about 65 gigabytes per second, and sequential writes was hitting up to 45 gigabytes per second for the larger I/O sizes. And then we also have things for random reads and writes, file per process. And you see the general behavior, lower performance for the small I/O sizes, and as we increase them, we get much better performance there. These tests were run with, I believe, for the single SSU, we run with 16 nodes. We had about 8 threads per node, and these are using a 16 megabyte RPC size. And on the right side are the results from the full system run, utilizing all of our scalable storage units. So these tests were run with 1,060 nodes and 16 threads per node. And in aggregate, you see for sequential writes, we are hitting about 9.4 terabytes per second, and sequential reads was hitting about 13 terabytes per second. And our target for these our goal was to hit about 10 terabytes per second. For the random file per process tests, we don't have results for all the different I/O sizes. There were just sort of 2 tests that were run, one for a smaller size and one for a larger size. Those tests were also run with a much bigger chunk of the file system. We used almost 9,000 nodes for that with 2 threads per node. And you can see on the high end there, we had random writes that were up to 10.5 terabytes per second and random reads at about 14.7 terabytes per second. And we did a similar thing for the capacity tier for the disk-based OSTs. On the left, again, is a single scalable storage unit that would comprise the 2 OSS nodes that have 4 disk-based OSTs in them. The single SSU test used 16 nodes with 8 threads per node, and you'll see that sequential reads and writes were fairly steady across the I/O sizes. Sequential writes getting up to 23 gigabytes per second, and sequential reads hitting 32 gigabytes per second. Our targets for those were, for writes were about 20, and for reads were about 24. So we had easily surpassed our target numbers for that. And on the right, you'll see the results for the full system on the capacity tier. So those tests were run with 1,060 nodes, 16 threads per node. And again, sequential reads and writes fairly steady across various I/O sizes. We see sequential writes about 4.9 terabytes per second, and sequential reads up to 5.2 terabytes per second. Our targets for those were 4.6 for write and about 5.5 for read. So we surpassed our targets with the writes and just slightly under for our reads. For the random file per process results, it was the same 1,060 nodes but only used 8 threads per node for that. And here we see that the random reads and writes increase, and you'll notice at the end we have, for the 16 megabyte I/O sizes, we get numbers that are quite a bit higher than the sequential ones, which we believe is a bit of an anomaly. I was talking with Dustin, he explained that these, for all these tests, we typically did 3 iterations, and what's shown here is the mean of the 3 iterations. The last data point for the random file per process, he explained, was actually just a single run, and it was because the subsequent runs were beginning to fail, and he said they had been seeing odd behavior prior to that, so he believes that those last 2 data points may actually just be an anomaly because they are much higher than we expected for that. So we're not entirely confident of those last 2 numbers there, but we included them for completeness with the others. And then one of the other tests that we performed was we wanted to see how well the performance was using our default file layout. For a lot of these other ones, you know, you can easily set up your striping to optimize. You go for the hero runs, you get the most bandwidth. But we wanted to get an idea of if users came on the system, they use our default layout with several PFL components, what kind of performance would they see, you know? And so we ran the IOR tests again, and I've listed the sort of default layout here for reference, and across the various I/O sizes. And you see we don't get, for the sequential reads and writes, we don't have quite the nice flat curve that we did with like the hero run numbers. You get a little less performance at the smaller ones, but it ramps up and you know, starts to level out. And I believe for those, you know, we end up getting like sequential writes that are now hitting about 4.3 terabytes per second, and sequential reads are up to like 4.9 terabytes per second. So it's not as fast as the file system could go, you know, but then again, you know, you are only utilizing, you know, for large files at the high end, at most you're utilizing 8 OSTs there. We're not hitting every OST in the system. So it's a relatively small section of the file system you're using for this, but we're still seeing quite good performance out of this. So a user that comes in and runs their code without tuning the file layout should see a pretty reasonable performance just using this default layout. And of course, you know, someone that actually understands their code, knows how it works, can obviously set their striping to maximize their I/O for their specific application. So in summary, we have Orion in production and being actively used. Several users on the system have started reporting some significant I/O speedups, and the general impression has been pretty good with the performance. We're still obviously working through some of the issues that pop up, working through some stability things because it is sort of the early production period. But right now, things are going along pretty well. The PFL layout that we've chosen seems to be working quite well for these use cases. So far, we've not seen any problems with our use of DNE, PFL, DOM, and things like that. And we're making use of the self-extending layouts to protect against OSTs that might fill up. And of course, we still have our ongoing testing and improvements that are being made, changes to things like network stability and that. And we're working on doing some policy engine testing for purging and file migration now that we're in production. There's the obligatory acknowledgement, and I would be happy to take any questions. I will preface this real quick in saying that this is normally the talk that Dustin Leverman would give if he were here, but he was unable to attend, so I'm sort of taking his place. So I'll try to answer what I can, and if I can't answer it, get with me afterwards. I might be able to find the answer for you here, and if not, I can put you in contact probably with someone who can answer your question for you.
Okay, I see two. Okay.
So going back a few slides, your default file layout performance, which was the last slide you had with the graphs on it.
Yeah.
So I was just curious. So with that, with the self-extending layouts, by the way, it's exciting to see someone using that. I wrote that feature. So, so with that 256 gigabyte extension chunk size, and then that write rate you've got there, you're going to be getting like 2 extensions a second. Did you see any performance costs? Did you try not having that, like not having the self-extending layouts for that? Just curious.
No, we didn't really try a lot of different ones. We had sort of pressed for time with some of the benchmarks. We were hitting some of the key ones, and it was sort of at the end, it's like, well, we think this is the default layout, so let's just make sure that this was sort of a sanity check of if we put this, configure this for users, is the performance just going to tank? Like, we just want to make sure, like, hey, we're not going to be messing things up by setting this. So as far as I'm aware, I don't think that Dustin had ran anything trying to compare the difference between the two. I mean, that would be an interesting thing to test to see if that drastically affects performance at all.
Yeah, I'd just be curious. In the hero run case, for a user who's writing at a slower rate, it wouldn't be a big deal. But for the hero run case, you might see something. So I'm just curious to know. So.
Yeah.
Just a quick question. This could have been in there, and I just missed it. I'm presuming this is direct I/O rather than buffered I/O, given the hockey stick at the end on record sizes.
No, I don't believe we use direct I/O on the IOR.
Is it buffered? Okay.
Runs. It should just be all buffered.
Okay, yeah. Cool. And is that reflective of what most of the users do?
Yeah, as far as I'm aware, it is.
Cool. Thank you.
So this machine and the mission of the machine that Orion is connected slightly different than a few other supercomputers out there. This is leadership supercomputer, which means we are catering to the large end of the scientific applications at large scales. We have smaller and medium job sizes as well, but the whole purpose of this system and the file system attached to it, Orion, is to cater to the very large runs. So yeah, this is probably typical user behavior.
I have a question.
Yeah.
So I like what you did with your default layout, but as a devious user, I would see that and say, I'm just going to set the default stripe for my base directory as put everything on Flash. Could you comment on any sort of policy you have or how you're going to prevent people from doing things like that?
Yeah, unfortunately, it's something with Lustre. You can't stop people from doing it. Like, when you define the OST pool, it's there. Users who are smart enough can query for it, and they could set a layout on it. We're looking at potentially, one idea tossed around was adding a wrapper to LFS set stripe that would basically intercept it and be like, hey, no, don't touch this. If you have basically kind of directly, if you think you need to change it, come talk to our user support so we can work with you to make sure that you're actually you really need it, and we can help set it up. Because we do know that I believe some people have worked with some of the early users with their applications, and things like single shared files and stuff like that. Like, clearly the default layout's not optimal for them, and we have worked with users to choose a different layout from that default that will better suit their needs. I don't know what the status is with that wrapper and that too, but it is it is a potential concern. I think a lot of it is going to revolve around user education and probably relying on the fact that most users, if they don't take the time to restripe from the default layout, they're probably not going to go looking around and mucking with things. And part of that, I think, is just going to have to be monitoring of the utilization of this and trying to catch users who might be trying to game the system and dump everything on the performance tier.
Actually, the better solution is OST pool quotas. So that's a way to restrain our users from doing that kind of behavior.
Yeah, it wouldn't stop them from using it, but we could limit potential damage from someone like filling them up and just dumping everything to it too.
Yeah. So that would stop them from doing that.
Yeah,
And
it's-
it would force it. We also have a policy tiering engine that we've been working on, and that's probably a good use case of that for when we implement our migration stuff. So users can do that, and then our policy engine will eventually see them do that, and then it will relay out their files, and they won't even know we did that. And so that's the plan, is to basically rework everybody's files when they're not looking.
Yeah, it's a lot of this is the theory, and then now we get people on it, and it's going to be as people really use the system and we monitor things and gather real world data on what's going on, that will inform our future decisions. And so some of these things may change as we discover how people are actually using the system or want to use it as well.
So it surprises me a bit that your last component is only 8 stripes, right? Given that it's already, files over 128 gigs in size, and you have 450 OSTs, that you wouldn't stripe it, like 60 or 100 wide in the last component, because you're going to get a lot of capacity and hopefully bandwidth, out of that.
Yeah, that was a tough decision of trying to figure out how wide should we go, because we could have gone extra components and gone like 1 and then 8 and like stepped up, but we didn't really want to get a large number of PFL components, and then it's like, well, do we jump from 1 to 100? And we were looking at, well, we were also trying to balance what we expected is from clients, like how much bandwidth could you get, like how many OSTs, how wide should you stripe it to get a reasonable amount of bandwidth to it. And we felt like, with our performance numbers, 8 OSTs would actually still give a pretty decent bandwidth to these things. And like I said, like this is the default. It's not, you're right. It's like, if you want better performance and you have a large file, it's like, yeah, you should really be changing it. This is just there. And there's a certain sense of like if you can't be bothered to change it, don't complain too much if the performance is not great. Like if you get to that point, you really should be looking at changing that striping layout and possibly going wider if you need it.
From the few early users on the system, the initial feedback we were getting was short of love letters to the supercomputer and the file system. So users seem to be extremely happy at this point. They can figure that on their own.
So the connection to the Slingshot network is Lustre treating, because it sounded like it's basically direct connected. There's no LNet routers, so is that being treated as an Ethernet endpoint?
So it is direct connected on the fabric. We do have LNet routers. Those are intended for other systems at OLCF to connect to it, because Orion will be considered a center-wide file system. So we have a bunch of routers that we can use to make the Orion file system available to other clusters that we have. But from Frontier's perspective, it's direct connected.
So Orion thinks it's using the Ethernet part of the stack. It thinks it's on an Ethernet network, but really it's
It uses the
Slingshot.
KFI L&D driver for all of its access.
So we have gone multiple iterations of it, from Titan to Summit to Frontier. We have tried different versions of how the file system, center-wide file system, should be attached to the supercomputer. This is the 3rd iteration. Previous iterations were loosely attached, routed, and then on the same fabric with the supercomputer, this one. So we are trying.
Do we have any more questions for Rick? let's thank our speaker.